What we want to look at now are other types of functions that we can graph and how these functions interact with the space that we're mapping everything towards. And so what we're going to do is we're going to look at some different systems: exponential functions, quadratic functions, and logarithmic functions. And so one of the things we're going to look at, and I want to do a thing that I don't like here, bear with me 2 seconds, is I'm going to get us into this data realm here. Let me fix how this goes through. I normally don't like, oh, it dropped out on me here, doing slides, but let me make the slides fit. Let's see here. 2 seconds. I'm going to get all of this to fit on the screen here. Take me a minute. Sorry, I'm trying to get my screen to fit on here for you, and it's not. There we go. And let me just make this the right size. This here. Alright. My apologies. And I'll talk over this here. I'm not a big fan of talking to slides, but there's some graphs here that instead of making them by hand, we can do. And what happens is, in the real world, we measure things. And in this case, we're going to look at what are called scatter points, scatter plots, which are a collection of points. And each point represents a piece of data. And when you have a scatter plot, you can have a line or a line of regression that cuts the data in half. By the regression line, half of the data is above and half the data is below. And we can use this line as a relationship to predict future behavior. And so scatter plots use regression lines. One of the things that can happen is we can get different types of data that model across. And so this is linear. And so there is an equation of a line. I could take a couple of reasonably, so let's see, 70 and 100 and 30 and about 200, and I could plot the slope, and I could plot an equation of this line, and I could predict the percent of adult females who are literate versus the, what is this, under 5 mortality, right? And so female literacy versus the mortality rate per 1,000 for under 5, and how education helps keep mortality rates down. But again, it's linear, and we've worked with linear models. But there are some other models that pop up, and one of them are called exponential functions. And we've worked with exponentials before, where we have some base, and the base goes to a power. And so let's look at what exponential functions look like. So we'll come back over here, and we'll go to our graphing utility. And we'll make some exponential functions. So an exponential function is some base. So we'll have f of x equals, and let's say it's something that doubles. And so that's what an exponential function looks like. It starts off when x is 0. It starts off at 1, and it grows rather quickly. That's an exponential model. It has a steep curvature to it. We could look at a different base. We'll look at 10 to the x. And notice it starts at 1, but this one grows a lot more quicker than 2. And so exponential models have this kind of what they call hockey stick curve to them. They move and then they curve rather quickly upwards. And that's another exponential model we see. We sometimes see e to the x, which is a common because e is a natural number. And we get that green line there. And so this is what exponential models look like. They have this sharp rise and flat with an accented curve and a very sharp rise. All right, oops, that's the blackboard. Let me back here. And so these are the requirements for an exponential model. We have y equals some base to x, or f of x equals b to some base. B is going to be positive, other than 1, and x is any real number. And so now we can graph these by creating a table of values. And so if I have 2 to the x, if I put in -3, I get 2 to the -3, which is 1/8. And so my x values is -3 to the 1/8, or -3 for x, 1/8 for the y. And we do the same thing. We make a table of values. We write down each x value and we put it into our function, and we get the y value, and we make a graph. So I will think that and then we plot these. I would recommend strongly going to a web page like Desmos or using your graphing calculator. So let me pull Desmos back up. And please, oops, pull Desmos back up. There we go. And here we have the function of 2 to the x, which matches what we could do by hand. Right? When we had -3 was, highlight -3 here, come on -3, and I should get 1/8. There I do, I get 1/8. And so that matches the points that we saw within the slide. Well, what we want to do with these is we want to recognize that when we get data, we can get different models. And so if we have data on this population graph, and we take the peaks of these graphs and plot them as points, we can look at this point and we can see if it's linear or if it's exponential. Now what your book does is it uses inside of a calculator a function called linear regression or exponential regression as a way of looking to get numbers or values out of these. What we want to do, is we want to graph these on Desmos and see the shape that we get. So let's just pull into our graph here. Let me switch screens. Alright, so I've got my graphing calculator here, and we'll pull it across, and I'm going to enter the data here. I'm going to try to get these centered here. So let me turn this on. Good. And let me get my data up. And so I'm in here. Now, unfortunately, I can't show both of these on the same screen, but we're going from the example in the book on the population. So if you look at example 2, and we're gonna use the points 1950 and 2.6, I believe, from it. Let me make sure I get these models right. Yeah, about 2.6, 1960 and 3. 1970 and 3.8, and so on. We're going to make this into a table of data. And let me see here. Yep, here we have. I have the data. The data is actually in the textbook on page 471. And what they decided to do is they decided to make this year 1, this year 11, and this year 21. So they start counting from 1 up. Let me put over here. Let's come back here and I'll show you what I mean. So So what they're doing here is they're turning these points into data points. And so this is 2.6, this is 3, this is 3.7, this is 4.5, because it's straight in the middle, and the little extra dots here tell you where you're at. This is 5.3, this is 6.1, and this is 6.9. And this is your 1, 11, 21, 31, 41, 51, and 61. And so we're going to turn those into points on our calculator. Let's go back to the calculator, come in, and let's see, I'm going to go into my data points here. And let me enter into the, there we go. Now we're into the calculator proper, and we're going to want to enter in our table of data. So we'll come into our data set here. Alright, my screen keeps pausing. So we're going to come into stat, we're going to edit, we're going to create a list. What we're going to do is in the L1 values, we're going to put our X values. So we have 1, 11, 21, 31, 41, 51. Sorry, my fan on my computer went a little loud there. 61. And so there I have all of my X values. What we're going to do is we're going to come over here and we're going to put in our Y values. So it's 2.6, enter, 3.0, enter, 3.7, 4.5, 5.3, 6.1, and 6.9. And so now I have two lists, L1 which is X and L2 which is Y. So we're going to come back to stats here, and we're going to calculate. So the first thing we're going to do is we are going to do the linear regression. Linear regression, and our X is L1 and our Y is L2. Come back down and we're going to calculate. And what we get is we get an A and B value. And of course I have these backwards from what we have, and I have no R values here. Let me go back. Might have hit the wrong one. Is there another linear regression in here? Different calculator than the one I mainly use. This is, let's try this one. And I get the A value and the Y value. What the A value means is I get that the line is 0.073392 times X plus B, and this is the equation of the line, which will make the model that we have. Which is also in the graph above. Alright, so I was able to do a linear regression, and I can make an equation of a line for it. Let me jump over here and show you what I mean. If we look at the output of the graph here, we see that this gives me the line that I want. And the A would go in for the slope. And so the slope is about 0.7%. And B is the intercept, so it intercepts around there. And that's what a linear model of this data would look like. And so I can write an equation for this line. So let's come over here and do that. So we could say that if this data was linear, y would equal 0.07. I'm only going to take 4 decimal places, so 39 x plus the b value, again 4 decimal places. I'm just doing that so that 2939. And that is the equation of the line to predict the data from the world population graph that we're looking at here. Okay, so we went back here. This is what we had. We had the world population graph. We keep jumping back and forth in the data, and we're trying to predict where it would be in future values. So we could make a 2020 prediction based off of this. Well, let's look at if it was an exponential model. And populations do actually tend to grow exponentially, so it's not bad to do an exponential model. So let's go back to our calculator here. And let's go back to stats. And over to calculations. And we're going to come down to our exponential model. And we'll get an exponential model. And we're going to say everything's the same. We're going to calculate. And now it gives us a y equals a times our base to the x. And so what that says for us, we'll come back to the blackboard here, is we could also have an exponential model that equals y equals a, which is 2.5770, because I'm going to keep it to 2 decimal places, or 4 decimal places, times my base of 1.0170 to the x. Now this is my base. And so these are the two models that fit the data. And one of the things we would want to do is we would want to find a way to compare the models, right? And in a lot of statistics classes, you'll look at different regression models and figure out how to get better values out of them. But these models we could use for predictive value, and we could use them. Now, let's go back to our graph here and show why we have this issue with the two models. If I look at this, we can see that there appears to be a slight curvature here. There's a slight curve to it, but it's also very close to linear. So you notice here, this data point has to curve up to get there. And if you do any, biology or population sociology, we tend to, exponential models match what we see and are very good predictors. But this is really, really close to being linear also. And so we would use both models until they started to fail us on those. And that's one of the problems with data models, is that if I were only to look between these 2 points, well, a line would be the best predictor. But if I were to look at this point to these points, there's a definite curve there. And so when we use these regression models, we have to play with different predictors. Sorry, I'm gonna lose you for a second here. All right. And so we get the two equations that we see there, and we're able to make the models from them. And so with those two equations, we can actually predict future behavior by looking at further years ahead by substituting in. And both of these seem to function well. Now, if we plug in the value for 2026, we see that we get these two different models. We get 8 billion for a linear model and 9.4 billion for an exponential model. And so the question that the book's asking is, hey, if we end up with 8 billion in what was 2026, which of these models is better, a linear or an exponential? right? So we compare the models to a world population of 8 billion in the year 2026. Well, we don't have 2026 yet. So if we got the 2026 data and we see that it is 8 billion, then in the linear model is better. And when we get to 2026 and if it's closer to 9 billion, the exponential model is better. And this is the thing we do as mathematicians working with data, is we go back and forth between what we predict and what we can measure. There is a very particular base, and I showed it to you when I was doing exponentials, and it's called E. And E is the natural base. It arose from some compound interest ideas, and it ends up solving a lot of different types of equations. And so we have a tendency to use E as a base in place of any other base as possible. So what we do is we tend to write functions like this, where we have the risk is equal to some multiplying factor times E to, this is usually called the rate, and then in however your independent variable. Now notice, if x was 0, E is 1, because anything to the 0th power is 1. And so 6 happens to be the initial value when x is 0. And then as you put in the multiplying factor, which is your concentration of alcohol, your risk factor goes up. Because anything past 1, this number gets bigger and bigger and bigger. It'll never be negative. And so this increases. So you start with a risk of 6 and you increase. And so that's what we see here, is your percentage of risk goes up as these values increase, and we put these in the calculator. The exponentials have an opposite function, which are called logarithms. And logarithms have a really neat shape to them, and that shape happens to appear its way out. Now again, we have a function. It's log to some base x. Now your calculator has a specific way of showing these, so let me come over here and show you what the calculator shows you. Let's get this guy back here, turn it back on, let's quit this. And so your calculator, if you can see where my arrow key is, down here you have this key ln and this key log. ln is for logarithms of base e, and log is for logarithms of base 10. And so if I go ln of 1, I get 0. And what this is saying is, let me switch screens. I'm sorry, I hate not having two screens on this. What a logarithm does is ln of some number. I'm actually going to write it this way so we can see it. Ln of y is equal to x. Is the same as saying x y is equal to e to the x. And so when I put in ln of 1, I got 0, and that's saying that 1 is equal to e to the 0. These two things are equivalent. And so logarithms are the way of going backwards from an exponential, right? It tells me what my x value would be if my answer was something. Just like multiplication has division, exponentials have their logarithms. And they each have special bases. So y at 10 to the x is the same as ln of y equal to x. Or not ln, log. And those are the two keys your calculator has, log and ln. mathematically, we can do any base we want. We could have log 4y equals x is the same as y equals 4 to the x. This base matches the base of the exponential. And so logarithms are your way of going backwards on these. And so we can graph logarithms with different bases. Here I'm going to jump over to Desmos and show you the neat secret of this and how these things were invented. Because there's no easy way to make a logarithm. These had to be invented by mathematicians using tables. What I'm going to do is I'm going to show you, here is our line y equals x. And it splits down the diagonals here. Now if I make a function that is equal to log base 2, there's log base 2. And look what these do. They're a mirror image across y equals x. Any exponential function, its log mirrors across y equals x. And that's the nature of functions. Functions invert themselves. And so the one that does the opposite of the other. So let's look at, we said we had e to the x as one type of problem. And we said ln of x was its opposite. And notice how these match each other across that line. But if I were to use log base 10, it doesn't match. Log base 10, over here, doesn't match the mirror of a base of e. If I change this to 10, they mirror again. So the log and the exponential invert each other. And things that invert each other split across the y equals x line. And it's just a thing that functions do. Oops. Keep hitting the calculator instead of this. And so you can plot these by working out each number that would come into them, or you can go to Desmos. But here is the neat part. This is what logarithmic data looks like. It is a slow curving away, and it eventually flattens out. And so we can get logarithmic data. In logarithmic data, we have log regressions. We can enter all the data in. And that's something you should look at in the textbook. But I'm not going to force you to do it. So the last one are quadratic functions. Now, quadratic functions make parabolas, and I've already introduced that to you back when I was just kind of introducing graphing in general. And quadratic functions have that vertex. I'm going to try to make my fan stop, so bear with me. I'm going to see if I can get that fan noise to stop. Well, I didn't get it to stop. I quieted down, but got chuggy. And so let's come over here. And so when we were looking at quadratic functions, and I talked about their roots, I also talked about that they had vertexes. And so they have some minimum or some maximum based on the shape of the parabola. And what we want to do is we want to find this point based off of the values that we get from the quadratic formula. And so what we're going to do is we're going to look at the symmetry. Now we can find the x value of a parabola. The x value of the parabola or the vertex of the parabola. Right, so we can write any quadratic function as f of x is equal to, reviewing from the first lecture in this module, but we can write any quadratic like this. And so if we want to find the vertex, so this is going to be the vertex, the x value is minus b over 2a. These values. And the number we get from this, we plug back into here, and that's going to give us the y value. So we usually say it's f of minus b over 2a gives us the y value. A lot of texts will write this as being the vertex equation, or the vertex, the way of finding the vertex. Let's do one. Let me see if we can make some sense out of it. Remember, vertexes are really nice because they're positives and negatives, are maximums and minimums. So let's see what we can do with the parabola. So we're going to look at a quadratic equation, and we're going to see what happens with it. So let's get x squared minus 2x minus 3. Let's go x squared minus 2x minus 3 is our function. And so we're going to remember that ax squared plus bx plus c is our quadratic form. So in this case, our a is 1, our b is negative 2, and our c is negative 3. And so because a is greater than 0, it opens up. It's a smiley face. And so our vertex is going to have an x value of minus b over 2a, or 2 over 2, or 1. So our vertex has an x value of 1. Now I drop 1 into the function, and I get 1 squared minus 2 times 1 minus 3, or 1 minus 2 minus 3, or negative 4. And so the vertex is going to be at 1 comma negative 4. And now I can start to graph this function because I know it's going to be at 1 minus 1 comma negative 4, and it's going to open upwards. And it's going to be symmetric around 1. Well, the other thing I guess I could do then is if I know it's opening upwards and starting at negative 4, I know it's going to cross the y equals 0 line. And so I can solve this using the quadratic formula. I can figure out where it's 0 by putting in negative b plus or minus b squared minus 4ac. So what is minus 4, 1 times negative 3. So that's plus 12, so that's 6, all over 2a. So that's 2. So it's 2 plus or minus 4, so that's 16 over 2. So that's 6 over 2, so that's 3. And 2 minus 4 is negative 2, so negative 1. And so we have negative 1, which is 2 away from 1, and 3, which is 2 away from 1. And now I have enough information to graph this. And so quadratics are really, really nice things to graph because they are great ways of modeling things in the real world that have maximums or minimums. Alright, that wraps up Chapter 7. If you have any questions, holler.